Hello, everybody. Welcome back to another discussion in dynamics. Today we have some things to do. First of all, the topic of today is kinetics in curvilinear coordinate system. Okay, we'll focus on that. However, before that, are there any questions about what happened on Friday on example 2? I hope you remember that we didn't have time for example 2. And I think I promised you on that video that there will be like a brief Q&A session. Any questions to example number 2? So that means that everything was clear on that video, or nothing was clear. No questions, really? You got it? You understood it? Okay. That was quick. That was fast. Thank you. Okay. Okay. So today Professor Sani asked us to do 2 examples. Example number 1, we will use NT coordinate system, and example number 2, we will use R theta coordinate system. Okay. Before that, there is a quick info session. Homework 4 is ungraded. However, homework 4 covers these topics. Okay, these topics, and also topic that we are going to talk on Friday. Okay. So in my opinion, I strongly recommend you to look at those problems. Okay, just try to solve them. Okay, and treat it as a practice before the main event. Yeah. On Monday there is a match. Yeah, you against us. Yes, we'll see. So make sure that you come well prepared. Okay. Yeah, I'm just joking. Yeah. But anyway, yeah. Even though this is ungraded, just have a look at it. Okay, and try to solve those problems. And quick reminders, practice makes progress. Remember that. Okay, that's all. Did I forget about anything? Or example number 1. Please familiarize yourself with the problem statement before we start our solution. Okay. So what do we have in here? First of all, the authors of that problem prepared a very, very beautiful isometric view. Yes, here is isometric view. Yeah, but beauty is subjective also. It's a beautiful drawing, and I prepared the same drawing but in a side view. Okay, so this is our side view, and what do we have in here? Aha, we have such I don't know, object that is rotating with omega, capital omega. Yes, capital omega points upwards. What else do we have in here? Aha, we have a collar here. Collar here, and that collar can slide on that rod, and we have a friction between collar and the rod, and that collar has mass m, and it has velocity. Yeah. So what do we have in here? Aha, we know weight, we know that radius r. Aha, this is radius r. We know that angle alpha. Here is alpha. And we know that coefficient of friction, and we know that capital omega is constant, has constant value. Okay, and they would like us to figure out when this collar does not slide. Okay, they do not want that collar to slide, and they would like us to find range of this velocity to prevent sliding. This is the problem statement, and this is our goal. Yeah. Any questions to the problem statement? If not, let's start solution. So I will not surprise you guys that we will start with FBD and KD. Okay, let's start with FBD, and let's focus on let's prevent sliding down. Okay. So this is what I'm gonna do. I'm going to draw this color. I'm going to model it as a particle, but I'm going to represent it as a rectangle, okay? This is alpha. And thanks to our technology, I can copy paste. And those of you who do not use like tablets or something that you cannot, sorry. Okay, on FBD, I will show forces acting on our color. I will start from the easy one. So there is mg. Any other forces acting on our color? Anybody wanna go for it? Zach. Friction, exactly. Friction is going to act this way. And we prevent sliding down, yes? So friction will act this way. And any other force? Normal force, yes. So this one? That's all? And you're Jared, yes? No, oh, it was you. I thought it was him. Yeah, sorry, John. So this is not the end, because normal force is indeed acting on that color, but this is only one of the components of that normal force. Where is the other one? Exactly. Yeah, Tom, you can. Exactly, yes. It's gonna come out of it. Yeah, here. RT. Let's call it. Yeah, that's it. There is no other forces acting on our system. And I said that we will express this in anti-coordinate system. Okay, let's use anti-coordinate system. So since our velocity, please don't write it right now, okay? This velocity points this way, right? So we already know how ut, which direction will ut be pointing, yes? So if velocity was this way, ut will be pointing exactly in the same way. Ut. Yeah. We also have un. And we have our old good friend k. That is civilized, so it always points the same direction, yes? Okay. Okay, we have our coordinate system, we have our positive directions, so let's now express our accelerations, yes? So this is MAT. They should be aligned, yeah, but I just don't have space in there, yeah? Just that black circle should be coincident with the red circle, okay? We have also MAN, and we also have MAZ. Great. We are done with FBD and KD. What's the next step? Equations of motion. EOM. So we're going to do sum of forces in the t direction, sum of forces in the n direction, and sum of forces in the z direction. Okay. Okay. So in the t direction, oh no, I have to project, yes? Something. Oh no, not really. In the t direction, there's only one force, it's RT. RT is equal to MAT. And this is positive direction, by the way. Now N has this direction as positive, yes? So now we have to do some projections. So let's do orange vectors here. So if alpha is here, I believe that alpha will also be here. So this component will be R1 sine or cosine alpha. This will be cosine, yes. And this one has no other choice, R1 sine alpha. Okay, and let's do red vectors in here. So this is alpha, so I bet that alpha will be here. So this one will be sine or cosine? The horizontal one. This one will be with, yes. Guys, it's high time to learn that, don't you think? Please. You still have 5 days, yes, till the exam. And also, it's good to know it for the rest of your life. Besides those 3 things I mentioned before the discussion. No. Okay, we did projections. Now we are ready to put our equations of motion, yes, in n direction. So we will have in here R1 cosine alpha minus TF sine alpha, and this is equal to MAN. And in the z direction, we have R1 sine alpha plus TF cosine alpha, and this is, oh, and also mg, yes, minus mg. Minus mg equals to MAZ. Great, we are done with our second step. I like when the equality signs are like aligned, you know. All right, so what else I would like to do? Maybe I would like to express in a smart way these values right now. AT, AN, and AZ. I would like to express them in a smart way. So, question to you guys, what is AZ right away? If you look even at that drawing. What is AZ? Perfect, exactly. This will be 0 because it does not move up and down, yes? So that color is basically doing these circles, yes, in this horizontal plane. It cannot leave the horizontal plane. It must be 0. Z must be 0, yes? So this is because color does not slide. It cannot leave the horizontal plane. Okay, so this will be 0. So that means that this entire equation will be equal to 0. Okay, so we are done with this guy. 33% of the problem done. Now recall that A can be always expressed in this chord in such form. A T U T in planar motion, of course. A T plus A N U N. Okay, and I bet that you guys remember, or if you don't remember, you have an equation sheet that this is equal to dv dt, and an is equal to v squared over rho. Okay, that velocity is constant. The velocity of our color is constant, so I don't even dare to ask you guys what is this value. This is 0 because v is constant. Perfect. And in here we have v squared over rho. So can you guys tell me what is rho? Exactly. Yeah. Can I scroll up the thing? Ah, yeah, it's r. Exactly. This is our rho. This vector is our rho, and it's constant, by the way, yeah, because the thing does not slide. So r will be constant, lowercase r. So rho is r. This is equal to exactly 2 feet, they told us, and this is constant. So many informations we have, yeah. So that will be basically v squared over r. Okay, let's plug our findings in here. Let's plug these values here and here. Here and here. So I'm going to copy a lot today, guys. Please be patient with me, please, okay? Thanks to the technology, I can copy. And instead of this, I can put in 0 in here. We also said that this value will be 0. And we said that this value will be v squared over r. Great. So first of all, check this out. We know that RT is 0. Okay, this is information we obtained. Let's focus on these two equations right now, okay? So we have two equations and how many unknowns? So I believe that R1 is not known. I believe that TF is not known. And I also think that V is not known. Dang. We have three equations, three unknowns, yeah? So we need third equation. And this is good moment before finding the third equation. This is good moment for questions, I think. I have a question. Do I speak too fast today? Is it okay? Not too fast? Okay. Questions to what happened so far? So we did FBD, KD, we created EOM, and then we used information from three weeks ago, yeah, where we figure out, then where we derived these things, yes, and we just plug them in here. Okay, this is all what happened. Just 3 steps. Can I continue? Okay. So where can we find the third equation? What do you think, guys? Scott. Sam. I was wrong already with your name. Don't worry. Yeah, go for it. Yeah. Yeah, static. So we have to look at friction. Yes, exactly. So we are in static friction case. Static friction case. TF is lower or equal than mu s n. And by the way, n is a normal force. N is normal force. And our normal force has 2 components, yes? R1 and RT. So our N is R1 squared plus RT squared square root, yeah? However, look at the top of that board right now. RT is 0. Yep. So our N will be exactly equal to R1. Great. This is first thing. And second thing is that we are looking for V extreme, yeah? They ask us to find V minimal or V maximal, yes? V extreme. V extreme, or I will call it just V ext. So for this case, our TF has to have maximal value. TF max is equal to mu s R1. Because we are looking for the extreme value of velocity. And that's it. And Sam solved that problem basically, yes? Yeah, that's it. Because thanks to him, we have 3 equations and 3 unknowns. Exactly. Okay, all of a sudden we have okay, guys. So yeah, and this is solvable. This is solvable. This is our equation 1, equation 2, and equation 3. So you can solve it at home. I'm just going to give you a solution, okay? Because I know that you know how to solve probably even 7 equations and 7 unknowns, yes? So from equation number 2, if you solve it at home, equation number 2, you will obtain R1 that is equal to mg divided by sine alpha plus mu s cosine alpha. And if you plug in values, you will obtain that R1 is approximately 0.5489 pounds. Okay? Now, V extreme from equation 1. You will end up with plus minus R over M. This will be everything under square root, okay? R1 cosine alpha minus mu s sine alpha. Okay, plug in values. I would like to plug in values here, okay? Just maybe some of you will have a question on what happened on the board. So that would be 2 divided by 0.5 divided by 32.2, 0.5489, cosine 40 minus 0.35 sine 40, and everything under the square root. Okay, so this is how our equation looks like after plugging in values. Grab your calculators and obtain that our V extreme is equal to approximately plus minus 6.1849 feet per second. And our velocity has no other choice. Our velocity vector has no other choice, but it has to look like that. UT, okay? UT is always aligned with it. Okay, this is V minimum, by the way. V min. End of part 1. Now, V max. But it's a good time for questions. Any questions to what happened on the board? Draft. Yeah. Drew. Okay, sorry. Oh, that's a great question. Yeah, I forgot to say that. Because we prevent sliding down. We prevent sliding down. So if you look at that drawing, yeah, so imagine what will happen if the velocity is 0. Velocity is 0, what will happen with the color? It will slide down. Yes? So then you will increase the velocity, keep increasing, until you reach the minimal velocity that it will stop sliding down. Okay? And what will happen if you have your velocity is very large? It will start moving upwards, exactly, because of the centrifugal force. Exactly, yes? So in order to prevent sliding down, we can deduce that it has to be V min. Now V max. Yeah, we're going to find V max. Okay, any other question? Thank you for that question. It was a good question. Okay, so I like technology because part number 2 is exactly the same as part number 1 with one more difference, with just one difference. Yeah, we are going to flip one vector on FBD and that's all. So I hope, guys, that you are not going to hate me, especially guys with pen and paper. I'm going to copy all that drawing. I'm going to copy the drawing. Remember that I'm recording, yeah? So this will be on YouTube, yeah? So even if you don't make your note, if you don't finish all of your notes today, it will be on YouTube, yeah? So we will end up with everything the same besides one vector. And that vector is friction, yes? So prevent sliding up this time. Yeah, we're going to prevent sliding up. And TF is not going to acting upwards. This time TF will act this way. Okay, I'm going to move that MG somewhere else. And everything else stays the same. Everything else is exactly the same as last time, just TF flips. Okay? So let me do these projections. So we have this red vector and this red vector. And if alpha is here, I bet that alpha will be here. So this one will be TF sine alpha. And this vector will be TF cosine alpha. That's all. That's all the difference. Okay? So please don't hate me more. I am going to copy paste equations of motion. Yeah? Because they will look exactly the same besides one small difference. Opa. So we will end up with exactly the same equations of motions. Besides sign in front of TF. Every component with TF will have different sign. So in the second equation of motion, oh, wait, I forgot about this. TF sine alpha is multiplied by minus. Switch it to plus in this case. In here we have plus, we have to switch it into minus. That's all. That's the entire difference. So if you understand part number one, you can do part number two. Okay, next step, exactly the same. AZ is 0, exactly as I think it was Brian who said that. Then AT is exactly the same, 0. And also AN is V squared over R in this case, yeah. So plug these three guys here, here, and here. Next step, exactly the same. So I'm gonna do it. And then Sam said earlier that we have to go for friction. And we're gonna go for friction one more time. So TF maximal, TF extreme is equal to mu S R1. And again, we ended up with 3 equations and 3 unknowns. And you are able to solve it. So expression for R1 is exactly the same with one difference. I'm going to copy paste equation for R1. Why not? This is a equation for R1. In this case, just flip that sign. Plug in values and obtain that R1 in this case is approximately 1.3345 pounds. And equation for V extreme is exactly the same with one caveat. Please copy paste. So in here we won't have minus in here, but we'll have plus. Grab your calculators and obtain that our V extreme, in this case V maximal, is approximately 13.0514 feet per second. And this is V max. I forgot about plus and minus, yes? Here, plus minus. I will ask you about that plus and minus in a second. So our answer is following. V, to prevent sliding, V belongs to 0. What I'm talking about, 6.1849, 13.0514 feet per second. And this is the answer. That's all. That's the end of the problem. Any questions? Why do we have plus minus here, by the way? Why? What does it mean physically? Exactly. Our thing can rotate either this way or the other way. And the dynamics will be exactly the same. Exactly. Thank you, guys. Okay, questions or example number 2? Vince?
I just got a hypothetical question. If the friction if the static friction coefficient was smaller, would that range of velocity also be smaller, in which it would stay? So the answer there was
I understand the question. Yeah, let us look at the equations. So this is the answer to your question. You must at home use your computer to plot this expression. You see, because this is basically velocity as a function of mu s. You see? So this is how velocity depends on mu s. Okay? So you should plot this at home. If you don't know how to do it, you should learn how to do it. Okay? This is my answer to your question. I don't know. I don't have a feeling for that, but I would know after plotting that function. Yeah, or just plot it in Wolfram Alpha. There is like a website, Wolfram Alpha. Just put that equation there. They will give you a plot for that. Okay. You seem like confused. No,
no, I'm thinking about it.
Okay, that's deep thinking then. Okay. Any other question? It's hard to read people's feelings, or like when you have that thing on your face. Yeah, sorry. Okay, example number 2. Please familiarize very quickly with the problem statement before we start our solution. Can I have the attendance list? Like 3 ghosts. Christina, are you here? I don't see you. This is not Ivan? G? No? Okay. Okay, guys, what do we have in here? First of all, we have one mass, yeah? This is our mass. And at the very beginning, it is located here. So this is our position 0, yes? This is our R0. R0. What else do we have? Aha, that color is, again, stuck on the road, yeah? And we have no friction this time. We have no friction between road and the collar. However, we have this cable. Yep, this cable here. And this cable will kind of replace the friction there. Yeah? This will like produce that force, the horizontal force. And that cable, we know that cable is being wrapped around this winch, they call it? Yeah, they call it winch. And that winch is rotating with small lowercase omega, and it has radius b. And the entire structure rotates with capital omega around k direction. Okay? A lot of stuff is going on in here. Okay, what values do we know? We don't know any values. They ask us for a symbolic solution, yes? So we know only symbols. We know just some parameters, but we don't know their values. And they ask us to find this tension in the cable as a function of time, and also reaction force between collar and the rod as a function of time. Questions to the problem statement? Solution. I'm not going to surprise you guys. I'm going to start with FBD very quickly, okay? FBD and KD. So let me draw that collar. Let us model it as a particle, but let us also draw it as a rectangle, okay? And we'll express everything this time in polar coordinate system, okay? Polar coords, or r theta coords. Okay? So let me introduce it. Aha, so if this is our position, yeah, if this is our position R, I believe that this will be our UR. Yeah, and the entire thing rotates this way. And U theta is always on the right, on the left-hand side of UR. So U theta must be pointing this way. This is U theta. And here is our old good friend K that always points in this way. Okay, let me also copy that for the KD. And I'm gonna draw the most obvious force here. And you guys are gonna tell me the rest, okay? Mg is acting on our thing. There are two other forces that act on our thing. What are they? Tension in the cable, perfect. Tension. And there's one more. John, repeat what you said half an hour ago. Normal force, yes, exactly. This way? And? Into you, okay. Or into the board. Let's do it into the board, yeah. Yeah, this is progress. You see? Yeah, we have normal force that has two components, exactly. Okay, so now our accelerations. We have MAR pointing this way, MA theta pointing this way, and MAZ pointing this way. Great, we are done with FBD and we are done with KD. Now, none of you is surprised, equations of motion. So we have sum of forces in the R direction, sum of forces in the theta direction, sum of forces in the Z direction. Okay, in the I direction, that was the positive direction, yes? Plus. So what do we have in here? Minus T only. Minus T is equal to MAR. Now, in the theta direction, this is positive direction for us. So we will have R theta, and this is equal to MA theta. Now Z, this is positive direction. So we will have RZ minus MG, and this is equal to MAZ. Brian, was it you who said that MAZ is 0 last time? Yes, so what is the value of MAZ 0 this time? Sorry, AZ? It's also 0 again, yeah. So exactly what Brian said, this is 0 because our collar cannot leave the horizontal plane. How about two other accelerations? Do you remember this expression? AR UR plus A theta U theta. So AR, if I remember correctly, was equal to R double dot minus R theta dot squared. And A theta is going to be equal to 2R. This is Coriolis, and this is tangent. Okay. So now let's find values of these two guys, okay? And let's plug them here and here. Okay, let's do it. So you guys just please help me in finding what is R, R dot, and R double dot. Okay, and also what is theta dot and what is theta double dot. So let's start from easy things. Let me copy this very quickly. So if you look at that picture, guys, what is value of theta dot? If you look at that picture. Sorry, yes, AJ, yes. Perfect, perfecto. Yeah. And by the way, it's constant. Yeah, you can see it on the drawing. Yeah. So I don't even dare to ask you guys what is theta double dot. Yes, because you would like all leave here. Yes. This is zero. This is zero, obviously. Yes. Okay. How about this guy? How about this guy? R dot. If you look at that picture. So this is our. By the way, R dot tells us change of rate of change of this vector r. Yeah. So r dot will be basically this velocity, this way. This is r dot, that blue vector. Anybody? Let's give him the, yeah, Brian. Yeah, it can start at rest, but this is not what I'm asking for. I'm asking for velocity. Yes. Yeah. And Trevor, you are very, very active, so I'm gonna go for Marcos. Yes.
Whenever the symbol is on the
Okay.
I do remember.
It's fine. Yeah. And okay, so whatever the symbol times. You're awesome, man. It's the best answer. Thank you. There is a new person here. Okay, Calvin. Times not time, but small omega times, and I want Ben. Perfect. Yes. You see, together we solve it. Yes, exactly. Okay. And Marcos, you're great. You should think like of, I don't know, stand-up comedy. It's whatever that is times. I don't know. That was awesome. Yeah, it really made my day. Okay, and this is also constant. Yes, omega times b is also constant. Yes. So yeah, I see Vince. Wait a second. So this is 0. And if we integrate it once over time, we will end up with initial length minus omega bt. Yep, this is what we're going to end up. Yeah. So now we found these values. Okay, you have still 5 minutes. I think I can squeeze one more question. Yes, Vince, you had a question? Perfect. Thank you. You're correct. Yes. You're right. Yes. It should be negative. Yes. Thank you. I made a mistake. There should be negative value here. You know that I made that mistake last hour. Nobody corrected me. So I'm going to let them know. Okay, so now let's plug these values back in here. So we have AR that will be equal to what? I believe it will be minus L0 minus omega bt omega squared, and I theta will be 2 minus 2 omega b omega. Yeah, these are our values. And now let's plug this in our equation of motion. Plug into our EOM. Okay, so don't hate me, guys. I'm gonna copy it. I'm gonna copy these things, all these 3 things here. And I think that you guys told me that this is 0. And you also told me that this should be minus m L0 minus omega b t omega squared. And this should be minus 2m omega b omega. Great. So we already can see that our RZ, this reaction force, is always mg. Yes? And if I remember correctly, they ask us to express t as a function of time and also r as a function of time. So we are like 60 seconds from the solution, guys. Because once we have these 3 equations, yeah, 1, 2, and 3, we can take basically the first equation and we can write that t is equal to m L0 minus omega b t omega squared. This is the end of part 1. This is exactly t as a function of time. Yeah, t as a function of time. How about part B of that problem? They told us to find R, reaction force. Yes, so R will be R theta squared plus RZ squared. And we have expressions for these two values. So let's just plug them in. So R will be 4 m squared omega squared b squared capital omega squared plus m squared g squared. I think we can even put m in front of that square root, yeah? So R will be m times g squared plus 4 omega squared b squared omega squared. This is constants, yeah? That's it. Answered part A, answered part B. Answer A, and this is answer B. Questions? How do you like these problems? Yeah? Guys, we have like 20 seconds. Can you please, so what my goal today was that, first of all, homework 4, look at it, okay? And please maybe use this recipe to solve these problems, okay? So observe that in example number 1 and 2, we follow that recipe. Yeah. First one, we draw FBD plus KD. Yes. Once we have that, we are able to put EOM. Yes. And usually, 99% of the time, not always, but 99% of the time, we have to calculate number of equations and number of unknowns. And 99% of the time, number of equations will be lower than number of unknowns. We will have too much unknowns, yeah, to solve our problem. So, what would be step number 4? Find more equations. Yes, find more. And where can you find it, guys? For example, friction. For example, friction. Or, for example, kinematic constraint. Yeah, like a rope. Yeah, or kinematic constraint. And once you have the same number of equations and unknowns, then just do algebra and you are done with the problem. Yeah, algebra. Yeah, sounds like easy points on the exam. Follow that recipe, you will be good. Have a good afternoon. Sorry for stealing 1 minute of your time. Have a good afternoon.